Okay, so um, let's talk about this first. When you have questions like this, like one that has like 3 questions, it's good to understand the situation first. Now, drawn to scale, so it says the elliptical orbit of a comet is shown above. Positions 1 or 2 are respectively the farthest, so 1's farthest away, and 2 nearest to the sun. At position 1, the distance from the comet and the sun is 10 times that of position 2. So what I'm going to do is I'm going to say R2 is equal to, I'm just going to call that R. And let's do this. So that means that R1 is going to be equal to 10 R. So we'll have an R right here. So let's think about what that implies. Now I'm going to show you an equation, and I'm going to seem to contradict something I said just a few, like in an earlier video. I think like the one right before this. All right. U, capital G, Esteban, this is where you use this one, the gravitational constant times mass 1, mass 2 over R. And then this, if you notice, has a negative in front of it on the equation sheet. Okay, I know I said energy is not, you don't want to really totally consider it work. Actually, though, I think the equation sheet might, I do not have the equation sheet in front of me, might say delta, which would imply work. But even if it doesn't say delta, sometimes you'll see it in textbooks and stuff written this way. It is implicitly delta. It is implicitly the work it takes to overcome the gravitational field at a distance, like to get a satellite in orbit. And since this is like, it's basically this negative is to let you know that it's like the work done against the gravitational field, or against the gravitational force, however you want to look at that. So it's just a convention to put this as negative to let you know, basically, that you put something into orbit, and that like you had to overcome gravity to do it. You could get into analyzing it and the, I don't know, arrogance or whatever it could imply, but you don't have to do all that. Just basically know that this is also implicit, that this is work. It's not just randomly saying that energy is equal to that, but that it seems to be really important to people that you know that you've kind of launched something, but that it's still being acted upon by a gravitational field like that of the Earth. Anyway, it's late. Sorry, I'm getting all philosophical. Okay, so anyway, this is like everything's based on this equation. You still treat it like your conservation of energy thing. So it's just what's turning into what's a little bit mushier here. Like, you'll see. Okay, the elliptical orbit of a comet is shown. Okay, so we got that. Okay, so 22 at position 2, the comet's kinetic energy is what? Well, let's look at just like what's happening speed-wise around here. Basically, your kinetic energy at any given point is going to be equal to this UG. That's what I'm saying. Like, it can be like kinetic energy going to this, or this going to kinetic energy. It's not so much like going down a ramp where it's like gravitational potential energy goes into kinetic energy. You can just, however you want to set them equal. I'm going to do them this way. So what you can say is, therefore, 1/2 mass speed squared is going to be equal to gravitational constant, mass 1, mass 2 over R. And I guess if you're looking at, your comet, you can scratch out one of these masses. So you'd end up with like v squared over 2 is equal to, it's a lot like your gravitational thing, I guess sun in this case, over R. All that's well and good. What I want to show you is this. V squared is directly proportional to the inverse of R. That's important. Or I guess you could say K is inverse to the, since they're just looking for kinetic energy, this will be important in a second, though, that's V squared. Since K, yeah, at position 2, the comet's kinetic energy. So basically, this is saying the inverse, so where it's closest, it's fastest, and that's where the greatest kinetic energy is. So it should be at 2. Or 2 should be where the greatest kinetic energy is. So it's not the same, it's not less. It's at its maximum for the orbit. So the answer for that is C. Okay, so 23, hopefully this one will go a little bit faster. 23 is wanting the ratio of V1 and V2. Now look, another squared thing here. I'm going to show you why the squared's not important. Okay, I'm going to change this to the ratio of V1 squared to V2 squared. So really the squareds don't matter, but I'm just going to leave the squareds because I have this nice equation here. Not equation, I have this nice like proportionality. All right, so for V1, this is going to be, you're at what, 10R, right? So V1, think about it, you're going at a slower speed. How much slower? You're going at 1/10 of your speed, basically. So even though that's squared, the 1/10 of the speed is fine. So you're going 1/10, right, divided by 1, because this one's just 1R. So this would be 1/10 of your speed. That's B. Now for the next one, I will do this. Remember, this is FG equals G M1 M2 over R squared. This is basically the same thing. But anyway, what is the ratio of F1 and F2 at the comet on position 1 and 2? Okay, so basically with your force here, you're just looking at R squared. So FG is going to be directly proportional to the inverse square. Okay, so F1 is going to be 1 over 10 squared to 1 over 1 squared. All right, so that gives you 1 over 100 divided by 1, and that gives you 1/100. So 24 is A.